Good afternoon, everyone. I want to first thank you all for attending our presentation today. During these unprecedented times, I hope everyone is staying safe and healthy. Today's presentation will focus on the real-world benefits and challenges of utilizing Bentley's OpenBridge and OpenRoads software for 3D modeling, design, and analysis. We'll go through the useful applications of OpenBridge and OpenRoads, including complex design, graphic development, multidiscipline coordination, and FDOT's latest workspace. With that being said, let's go ahead and get started. So my name is David Lutz. I'm a structural engineer with WGI in the Tampa office. In my 8 years at WGI, I've had the opportunity to work on complex steel bridges, complex concrete bridges, toll facilities with Florida's Turnpike Enterprise, as well as every type of miscellaneous structure.
My name is Callie McNeil. I have been with WGI for 5 years, and I've had the opportunity to work on concrete bridges, miscellaneous structures, and various projects with FDOT and Florida's Turnpike.
So the agenda for today's presentation, we're going to go through WGI's background. We'll talk about who we are as a company. We'll discuss historically traditional bridge design processes and its associated challenges. We'll then discuss several WGI products we've utilized OpenBridge and OpenRoads on. We'll talk about some of our observations and lessons learned, as well as some of the challenges we've experienced. At the end of the presentation, we'll go through some typical questions we've gotten during our previous presentations Q&A sessions. So a little bit about WGI, who we are as a company. We like to say we're a national firm with a local presence. WGI was founded in 1991 in West Palm Beach, Florida, where headquarters remains today. We have 22 offices nationwide with 12 located in Florida. We're a firm of 600 employees with nearly 400 in Florida. WGI proudly serves private clients, public agencies, and municipalities. We have won work with every FDOT district as well as central office. WGI is known for delivering design build projects, as we have won more than 45 projects valued at over $2 billion alone in Florida. Most recently, WGI was selected to lead a conventional 3D pilot project with Florida's Turnpike Enterprise, or FTE. With this project, WGI alongside FTE will develop 3D tools and processes to help with client review of 3D models. We'll develop QA/QC procedures as well as provide 3D information for permit coordination, public hearings, and higher level presentation material. We plan to accomplish this by referencing all design components of the project into one comprehensive model. We'll also be exploring the 3D benefits with FTE's maintenance department by providing additional 3D bridge information. So now we're going to discuss traditionally the roadway and bridge design process on a standard or typical project. Historically, traditional design has followed a similar path. First, your roadway engineer will develop the horizontal and vertical geometry. Then the structural engineer will come in and lay out the bridge based on that roadway geometry. Some preliminary calculations may be performed like vertical clearance, base clearance, site distance. The structural engineer will then coordinate with the roadway engineer if any revisions are necessary, like the vertical profile being too low, which typically triggers rework of the initial geometry. Once the initial geometry has been reviewed, the structural engineer would then proceed with the remaining bridge design, like substructure design, superstructure design, finish grade, and perform constructability reviews. During the bridge design process, we traditionally will have to take the geometric information from the 2D CAD and re-enter that information into various design spreadsheets and our design software of choice. Throughout this iterative design process, 2D plans production may begin and will be ongoing throughout the design process, but will require multiple rounds of revisions, which is dependent on our design and geometric changes. The obvious disadvantages of this approach is that you have manual data transfer with roadway and other disciplines. You have repetitive data entry between design calculations, spreadsheets, software, and plans. There's little to no change management when horizontal or vertical geometry is altered. There are no known translation issues between CAD, design software, and plans, and there's virtually no automation for CAD production or design. OpenRoads and OpenBridge combination tries to reduce or eliminate these disadvantages. OpenBridge Designer, or OBD, as well as OpenRoad Designer, which is known as ORD, look to remove the disadvantages I discussed in the previous slide and enhance the design process by continuously exchanging project information from the beginning of your project, initial geometry, all the way to final design. This exchange of information includes roadway geometry, bridge geometry, and even gets into the specifics like beam strand patterns and even bridge reinforcement. This all-inclusive approach looks to improve decision-making processes. OBD helps streamline real-time collaboration between disciplines, as well as sharing and repurposing data to minimize the risk of design errors. All of this helps us to identify early construction issues and ultimately provides a safer design. The advantages of ORD and OBD are you are able to leverage existing microstation tools like GeoPack and coordinate geometry. You have automatic data transfer between roadways, structures, drainage, and utilities. There is seamless and continuous updates when parametric data is changed, supporting immediate change management, such as horizontal and vertical profiles. We're going to discuss a specific example of change management on one of our projects later in the presentation. You can view your project layout in context of the real world. There's intelligent connection to design and analytics, including bridge design, rebar layouts, strand patterns, and vertical clearance. So you're able to reuse existing data for additional analysis. So these images you see here represent the easy-to-use and intuitive interface of OpenBridge Designer, also known as OBD, which we'll be referring to later in the presentation as OBD. This interface is very similar to MicroStation AutoCAD in that the ribbons and toolbars can be customized to your preference. We'll discuss some of the primary design analysis and reporting tools like the input report, create drawings, quantities report, and clash detection. We'll also talk about parametric definitions that are used to create bridge templates to be used in superstructure, substructure, and foundation design. Highlighted is the FDOT Workspace add-on within OBD. This add-on allows for plans production in accordance with FDOT criteria. Another important tool we will be discussing is a clash detection tool shown in the top left corner. The clash detection tool performs conflict analysis between the bridge and your user-defined, proposed, or existing infrastructure, which saves time, eliminates errors, and reduces project costs. You can view clashes in 3D or in table format, which can be helpful when checking the model, as well as performing QA/QC. This tool can also detect clashes with reinforcing steel and other embedments, in addition to checking horizontal and vertical clearance requirements. We will be specifically highlighting the clash detection tool in depth much later in the presentation.
These images represent the easy-to-use and intuitive interface of OpenRoads Designer, or ORD. Just like OBD, this interface is similar to MicroStation and AutoCAD in that ribbons and toolbars can be customized to your preferences. The tabs are set up so that you work typically from left to right. So you'll start with importing terrain and laying out the geometry. Then you'll move over to the corridors and model detailing tabs, where the tools used to create the 3D model are included. And then finally, the drawing production tab. We will discuss some of the primary design, analysis, and reporting tools throughout the presentation in one of our example projects. Throughout the presentation, we will continue to discuss OpenBridge Modeler and OpenBridge Designer and its capabilities. But first, I'd like to introduce you to Bentley's latest software, which includes OpenBridge Modeler. This software is called OpenBridge Designer, or OBD. OBD consolidates the modeling capabilities of OpenBridge Modeler and the analysis and design features of Leap Bridge Concrete, Leap Bridge Steel, RM Bridge, RM Bridge Advanced, and RM Bridge Enterprise to meet the design and construction needs of all types of bridges. The screenshot here shows an example of a bridge in OpenBridge Modeler. And this next screenshot shows an example of a bridge in Leap. With OpenBridge Designer, you have the advantage to using a single comprehensive package from beginning to end of any bridge design project. You can use one product to create an interoperable physical and analytical model for both steel and concrete bridges that can be utilized throughout the life cycle of the bridge. The image on the left depicts the design, analysis, and rating of a typical bridge. These programs leveraging existing MicroStation tools and interfaces. This is done by reusing civil data obtained directly from Bentley Road products such as Geopack, Bentley Inroads, or MX Road, and import roadway information and ground data from land XML files. The image on the right displays the capture of roadway geometry and topographic features similar to the Polk Parkway slides that David will present in a few minutes. The first thing you'll do when working in a project is create an OpenBridge designer file. This file will contain the OpenBridge Modeler files, LEAP files, drawing files, graphics, etc. Once you create an OpenBridge designer file, you'll choose if your project files will be in BIM workflow or standalone. A BIM workflow project must be done in the order of modeling the bridge in OBM and then exporting that bridge from OBM to LEAP. If you're working in LEAP and want to modify part of the bridge, say the footing depth, for example, you must update this in OBM. Notice in the top screenshot on the slide, the analysis button is not accessible. The BIM workflow option guides the user through the typical BIM steps. In a standalone project, OBM and LEAP can be completely independent of each other, where you can model your bridge in OBM or directly in LEAP. Notice in the bottom screenshot that the analysis button is accessible. You still have the capability to export between both software, but you don't have to keep the two connected.
Thanks, Callie. So one of our example projects we'll be discussing today is our Polk Parkway Design Build Pursuit. On this project, we were able to utilize OBD in several different ways, from graphics to design to quantities. OBD allows you to quickly and efficiently develop renderings for LOIs, LORs, and technical proposals. On this project, we modeled a two-span bridge with skewed substructure utilizing the existing microstation tools Geopack and coordinate geometry. We used OBD to develop our structural quantities by using the bridge reporting tools. OBD can develop various types of quantities like multiple classes of concrete, rebar, beams, piles, and more. You can also use it to develop independent cost estimates by manually setting the cost of that quantity. On this job, we used the FDOT area-specific historical costs and compared prices against the historical statewide data. We also used OBD to perform vertical clearance checks using the class detection tool. On this project, we were able to utilize one of the unique features of OBD, and that is the ability to use pier or foundation templates we developed from our previous job. OBD is fully integrated with ProjectWise, which is a good tool to support distribution with other project teams. We also developed 3D PDFs to facilitate conversations with our contractor, as well as in our internal team meetings. These 3D PDFs are also supported on mobile devices like iPads or iPhones for those who do not have access to a computer. Something also that's really important about this software is that Google Earth is fully integrated with OBD and ORD, which will provide real-world context for your models. At the time of this pursuit, we were unable to use OBD for plans production as the FDOT workspace was not available at that time. As you can see in this image, the model is not just a pretty picture, but is a real analysis and design tool. In this image, you can see the superstructure, substructure, foundations, and piles. You can also see the depth of the foundations, which we use to detect conflicts or clashes, as the program calls it, with existing or proposed drainage, as well as proposed and existing utilities. On this project, our proposed bridge was adjacent to the existing Polk Parkway bridge. As you can see, it's the bridge on the right is the existing Polk Parkway bridge, and the proposed bridge is the bridge on the left. So we used a digital terrain model, or DTM, of the existing bridge and as-built plans to model the existing bridge for real-world graphical representation of these twin or side-by-side bridges. Like I said, the bridge on the right is the existing Polk Parkway bridge, and our proposed bridge is on the left. One of the big questions we typically get is how do we check the models? We found several different ways to check and QC 3D models. On this project, we used the bridge reporting tool to print the input report for check and QC of the bridge geometry and design. We also performed a visual review to assure no gaps or holes between the ORD and OBD models. This is specifically important at the bridge approach slab interface with the roadway. You don't want any gaps between those two elements. In order to develop the graphics I've shown on the previous couple slides, there are a few steps required that we'll discuss now. The image shows the proposed Polk Parkway Bridge next to the DTM survey data of existing Polk Parkway. This shows the existing topographic and survey information, which we use to model the existing bridge, as well as develop graphics as I previously discussed. It's important to note, in order to develop the graphics we showed you previously, you must have existing or proposed elevation information. You will then take the existing aerials of that area, your project area, and drape them over the existing topo or vertical data. Once you've draped the aerials over the digital terrain model, or DTM, you can export the model to a graphic software program to put the final touches on your graphic. You can add features like different vehicles, landscaping, lighting. You can even choose your ideal weather conditions. Graphic software may be time and computationally extensive, and it's also not available to everyone. So another way to develop a similar graphic, as well as get the real-world context of your bridge, is to save as or export your bridge to Google Earth as a KML. Two important things is, when you are doing that, be sure to set your bridge to the correct geographical coordinate system, or else your bridge may end up in an unintended location like the middle of the ocean. There are also some vertical translation issues between OBD and Google Earth, like datum issues, and so you may need to adjust your model vertically to make sure you have the same datum and it's coming in at the spot you want. During the early stages of the bridge design, we wanted to analyze a couple different span arrangements and vertical profiles. As we all know, any change to the vertical profile or the cross slope has a corresponding effect on your bridge geometry and your design. Traditionally, this is an iterative process requiring pretty intensive coordination between multiple disciplines and redesigning on someone's part, whether it's roadway, drainage, structures, or all three. However, on this job, because we were using OBD and ORD, with every change of the vertical profile, the OpenBridge model handled the geometry changes seamlessly, as well as carried that geometry change through to the design software. It's very important to note that when you are modeling, when you're setting up your bridge, you must set it up using the parametric definitions, or any updates will not be automatic and they will require manual adjustments. On this project, the vertical changes were handled immediately and they were showing up immediately in the bridge model. This obviously increases efficiency and required less cross-discipline coordination. Another tool shown in the left image was the pier templates. Pier templates allow you to develop substructure and foundations quickly and efficiently. The multi-column pier we had actually previously defined on a previous project, and we were able to import that model and that template into this model for this bridge, and we site adapted it. Template-based definitions are simple and easy to use and allow flexibility as you move from job to job. Templates can also be applied to beams and decks, which help when the roadway engineers make changes to cross slopes or super elevation transitions. Another great feature of this program is highlighted in the image on the right. Originally, when we were first modeling the bridge substructure was modeled perpendicular to the superstructure and proposed Polk Parkway. However, to match the adjacent existing bridge, we decided to skew the substructure to be parallel to the existing road underneath Polk Parkway. We made this decision after the bridge model had been developed, but because we had modeled the bridge using parametric definitions, that means we linked the substructure and the superstructure together in relation to the alignment. This allowed, when we did make the change, this allowed for intelligent updating and change management. The image on the right, I know it may be a little bit difficult to see, but with a couple clicks, we were able to change the skew angle of the substructure from 0 degrees to 8 degrees, and the remaining bridge elements in the OpenBridge model were updated automatically. That means the beams, the bearing pads, the pedestals, joints, foundations, all the above were updated automatically with just changing the substructure skew from 0 degrees to 8 degrees. Like I said, the substructure and superstructure were automatically updated, not just in the model, but also in the design software. It should be noted that the 3D model will dynamically change the associated 2D views. Another important tool we use when modeling the bridge is the Copy To tool. Due to the symmetry of the bridge, after we finished modeling the first span superstructure, we use the Copy To tool to copy the superstructure definitions to the remaining spans. All right, so quantities, cost estimates, and bids are obviously a very important element of any design build or any kind of pursuit. OpenBridge Designer has the capabilities of reporting accurate quantities and quickly turning those quantities into a cost estimate. When you complete your bridge model, you'll be able to get the quantities based on your defined superstructure, substructure, and foundation. The quantities report is simple and very easy to use. This tool can be used to evaluate multiple substructure and superstructure alternatives based on your specific bridge model. You can compare different span arrangements with a click of the mouse. The steps are easy. Once your bridge model is complete with parametric definitions, I know I keep saying that it's very important to model your bridge with parametric definitions. Go to the Analysis and Reporting ribbon, click the Quantities report, and once within the report, you can import previously defined report formats. So if you have a previous project where you were able to fine-tune your report format and you got it just the way you like it, you're actually able to import that report format and use that on your future projects. Obviously, this saves you a lot of time and effort, and you don't have to keep reinventing the wheel and reformatting reports. So once you've settled on your format, simply select your bridge, shown on the left, or a unit of a bridge, and click Submit. A report will be generated in seconds based on your bridge model. You can also use this report as a quick check on your bridge model. For example, if you have an overly high concrete quantity, or a really high cost or an outlier of some kind in your report, then that is a good indicator that you may want to review your bridge model. The report can also be used to develop quantity plan sheets, or it can be submitted as a standalone deliverable. Currently, OpenBridge does not quantify rebar. However, you can export your report to a Microsoft Excel and insert a rebar ratio to complete any type of preliminary cost analysis. So we've talked about cost analysis on the reports, and here's a great example. It's a very helpful tool when you have predefined unit prices. However, there are many instances in which you will want to change the unit cost to get a more accurate and specific cost estimate specific to your project in your area or your state. There are several ways to change the unit cost, and I've highlighted two here. One way is to change the unit price by exporting the quantities to Microsoft Excel. In Excel, you can change the unit prices within the individual cells and update the total cost formula to get a more refined total cost. One thing to note is that when you do export your report to Excel, it will only export as numerical values. So there won't be any formulas in any of the cells. They'll just be values and text. So you will need to go into the cells and define the formulas and go ahead and do a little bit of the legwork. The second option is you can go into the material library and change the unit prices within the material library. And one good thing about this is once you change those and you save your unit library, you can use it on future projects. You'll do this by importing your material library as an XML from a previous project that has your unit cost that you want to use built in. This is also helpful if you are interested in modifying not only the unit cost, but the material properties on your bridge.
Another example project is the Colonial Parkway PD&E. WGI was hired to do the renderings and animations for the preferred alternative of this entire job. We constructed a model that spanned 12 miles and included all the proposed and existing features of the corridor. This is an example of a fly-through of the job. The video spans the first quarter of the Colonial Parkway and has live traffic. And I'm sorry if it seems a little choppy to you. In this video, you can see that we modeled all the existing buildings and landscaping. We coordinated with multiple divisions to bring this model to life. OpenRoads Designer and OpenBridge Designer were utilized to bring all the facets of the job together. After this video is concluded, I'll go into further detail about how each of the components were brought in to create a master model with all the disciplines. This animation was used for a public hearing to show how this project would impact the daily lives of the public. People could find their street and/or house if close enough and see if the project would affect their daily driving pattern. We were given positive feedback from the public saying that this made the project much clearer to them than the roll plots arranged around the room did. Animations such as this one will increase public engagement and help answer questions visually. So the first step in the colonial process was to use OpenRoads Designer to create the 2D line work and then use the corridor modeling to create a 3D model. Corridor modeling consists of creating templates within OpenRoads Designer. Templates are basically like typicals of the roadway that are extruded along the alignment and profile to create the 3D model. With these templates, we can model the entire roadway, barrier walls, MSE walls, guardrails, and more. As I mentioned previously, OpenRoads has a quantity component tool as well, which can make it very easily to pull quantities from each corridor and give an estimate very quickly. Similar to OBD, OpenRoads has the capability of tabulating quantities for specific components throughout the project. The second step in the process was to create the bridges, which was accomplished using OpenBridge Designer. We laid out the span arrangements, added the deck, the beams, the substructure, and the barriers, then referenced the bridge and roadway files into a master OpenRoads file. We looked over the merged model to make sure there were no gaps, inconsistent elevations, or conflicting widths between the road and the bridges. Since they were both developed using the same line work and profiles, the model flowed well and no issues were found. The third step was to coordinate with signing and pavement marking division to get their line work and sign locations. The pavement markings were applied by using a stencil tool in OpenRoads, which will make 2D line work and overlay it onto your 3D model. These signs were coordinated to go in the correct location and the correct elevation. All signs were created using guide sign software and manipulated to appear on the sign panel in 3D. The fourth step was to construct the toll gantry and toll gantry site. Due to the turnpike general tolling requirements, frequency, and vibration design criteria, the toll gantries were modeled utilizing a finite element software with necessary design capabilities. It's important to note that OpenBridge and OpenRoads are not able to analyze or design toll gantries. Once the model and the design were completed in the finite element software, we were able to export the 3D model to a microstation file and reference the microstation file into OpenRoads. Once the toll gantry was in OpenRoads, we were able to place it in the correct geometric location. Since OpenRoads and OpenBridge are able to relate to the real world, the gantry is presented in true context of its location. OpenRoads can be utilized to verify the toll gantry is meeting the horizontal and vertical clearance requirements with the roadway horizontal and vertical profiles. The last step is to create the surrounding areas of the model. For this, we use 3D freehand techniques to create the existing buildings and the existing terrain. You'll then export your model to rendering and animation software such as LumenRT or Lumion, where you can create still photos or long animations of your model. If you have exported your model to LumenRT and have already added objects such as people or cars, but need to make an update to your road or bridge, you can make these changes and re-export to Lumen without impacting the changes you have made within Lumen. Most animation software are also able to produce cubes. Cubes are a reduced version of your complete 3D model in a single file that can be delivered to anyone, whether or not they have the animation software on their computer. Within these cubes, the user is able to zoom in and out at any location along your model. These models can not only be useful for public hearings, but they can also be used for actual design and plans production of the project. You're muted, David.
Unmute. So on this project, Western Beltway, State Road 429, WGI partnered with Florida's Turnpike Enterprise to progress and improve 3D workflows, QA/QC, and design criteria on this project. This project is one of FTE's first fully integrated 3D model design projects for a mainline widening. OpenRoads quantity takeoff tools were heavily utilized on this 11-mile-long resurfacing project. We created 3D shapes within the roadway templates that were independent of the 2D design line work in order to obtain accurate quantities. The graphic on the right is an example of the template that was generated for this project. The surface course and friction course were created using different elements and levels so that the quantities of these two items were calculated separately, as shown in the screenshot in the middle of the slide.
This I-10 design build project posed difficult construction sequencing of 3 new box culverts, replacing 4 existing box culverts under I-10 in Jacksonville, Florida. Construction was to be done while maintaining water flow through at least 2 of the existing culverts at all times and maintaining traffic on I-10. This kind of construction is difficult to visualize, and potential conflicts can be easily overlooked with 2D line work plans. 3D models are a great way to help make important design and construction decisions, especially for the construction of this box culvert. Not only are the 3D models great for visualization, but are also used to create 2D contract plans. Over the next few slides, I'll go over how the model was created. But first, I'd like to show you an example of how a graphic from this project compares to 2D plans and the real world. Each of these represents construction of the box culvert during phase 1. The graphic clearly demonstrates to the reviewer how the water flow is to be diverted through 2 of the existing box culverts using sheet piles during construction. As you can see, the graphic is extremely accurate when compared to the real world. Here's a look at the phase 2 graphic in OBM before you export it to LumenRT. OpenBridge's freehand 3D solids modeling tools, which are shown in the screenshot below the graphic, were used to model the box culverts and temporary walls and anchors. OpenBridge makes it very easy to create miscellaneous objects at correct elevations and dimensions using the Civil AccuDraw tool shown on the bottom left of the taskbar screenshot. Within the OBM drop-down menu, the modeling menu has multiple tabs to help create solids, such as the box culvert in this example. First, a line was drawn from end to end at the invert elevations using the Civil AccuDraw tool. A 2D box was drawn at one end of the line to represent the outer shell of one of the culverts, and then extruded along the line to make a solid. Using the shell tool, the solid was hollowed out from end to end with a 10-inch thick wall. The anchors were created by drawing a single anchor in a separate model, saving that anchor as a cell, importing that cell into this model, and then once the anchor was placed appropriately in one position, it was extruded along a baseline that represented the sheet pile walls. The sheet pile walls were created in a similar manner. I would like to point out that OpenBridge Designer does not handle anchor walls nor box culvert analysis. So once the model was exported to LumenRT, we were able to change material features such as the existing roadway pavement versus the proposed roadway pavement, the existing box culvert versus the proposed box culverts, and the soil. We also added vehicles and construction workers. During the pursuit of this project, we were able to reduce the width of the roadway that was proposed in the RFP, which provided design and construction cost savings. We were able to highlight this in this graphic by adding the original RFP roadway design in red. As you can see on the right side of the graphic, we were able to propose guardrail instead of an MSE wall that the RFP called for. An important item to note is how the MSE walls are created in 3D. MSE walls are created with templates in OpenRoads, not in OpenBridge. This slide shows line work for a proposed MSE wall on I-10 in plan view on the left, the profile of the leveling pad of this MSE wall on the right, and the final elevation view of the MSE wall in OpenRoads on the bottom. The profile of the leveling pad was created within OpenBridge. Similar to OpenRoads, OpenBridge has a tool called Open Profile View, which allows the designer to select any smart line in plan view and create, view, or manipulate its profile. Once you are in the profile view, it not only highlights the line in plan view that you're viewing with the light blue arrows that you can see on the left, but also points to the corresponding plan locations with the light blue line when you are using the tools in the profile view. During this project, the roadway engineer was able to provide coping elevations, ground line elevations, and wall offsets to the structural engineer for the MSE walls. The structural engineer created profiles in OpenBridge for the leveling pads at each wall. The roadway engineer is then able to attach these profiles to their templates so that the leveling pads follow the correct profiles in the model and subsequently cross sections. If the profiles are ever updated, the model in OpenRoads would automatically update to fit the leveling pad profile. Note that the profile view is displayed in the direction of the stationing and is therefore the reflected view of the actual elevation in this case. As noted previously, the screenshot at the bottom of the slide is the actual view of the MSE wall with the applied profile in OpenRoads.
So as we know, 3D models help us evaluate complex situations, as Callie showed with the box culverts, that can be easily missed in 2D plans or 2D views. On this project, I-95 Commercial Boulevard over Andrews Avenue, we're going to highlight the clash detection tool when used to check vertical clearance. So on this project, I'm going to kind of explain the overall geometry, and then we'll talk about how we used OBD and the clash detection tool. So on this project, the proposed bridge was supported by concrete floor to I-beams and hammerhead concrete piers over multiple existing roadways in South Florida. Each of the existing roadways had their own unique as-built profile, which made the vertical clearance evaluation difficult to view in 2D. So after we developed the OpenBridge model, we brought in the existing roadway DTM file provided by our survey team to confirm the as-built roadway plans and profile. The DTM model did indeed match the as-built plans and confirmed that each existing roadway that the bridge was going over had unique vertical profiles. Without performing external vertical clearance calcs, which would require repetitive data entry, it is difficult to visualize any clearance non-compliance in 2D. With the clash detection tool, we were able to quickly verify both vertical and horizontal clearances. One very important note about this tool that we really want to drive home is that you must use the user selected objects and you manually select the clash detection criteria definition to any value you want. So if you want to maintain existing vertical clearance at 16 feet, 15 feet, whatever it is, or you want to check a sign structure at 17.5 feet or a proposed bridge at 16.5 feet, you will have to be the one to define that value within the program. You're defining what the tool is comparing against. The program can quickly check against vertical profiles or existing DTMs to identify if the bridge is meeting the bridge or sign structure is meeting the user-defined clearances. So as you can see above on this project, the pier was overhanging the roadway and was not accounted for in the preliminary profile. Thus, once we set the vertical clearance, the user-defined vertical clearance, the bridge was too low and was identified as a clash. This is a much more efficient process and less involved than a traditional bridge design process. This program can also be used in a similar fashion to detect for subsurface utilities or drainage horizontal or even vertical clearances by simply changing your user definition. You can use this tool to check clearances between different pipes or different objects. You can also use it for checking minimum fill requirements. Say you need 4 feet over utility, 4 feet over drain structure, whatever it is, you can use this tool in that manner. One drawback of the clash detection tool is that the program will identify a clash based on your user-defined value, but it won't tell you exactly where the clash is occurring. So you still have to use engineering judgment to further refine the profile by identifying those critical clearance points. So whether it's over the hammerhead pier or whether it's in the middle of a span or towards the end of a span, you still need to be able to kind of verify and use your engineering judgment to hone in on where your issue is and where your non-compliance is. This also applies to utilities and drainage. It applies to whatever you're checking against. I'm going to give a pretty good example of this in the next slide. So this slide demonstrates some of OBD's graphical capabilities similar to Polk Parkway, similar to the PD&E project on Colonial that we had. This example project, we were asked to develop graphics to show not only just aesthetics, not just a pretty picture, but also utility conflicts and make a real model out of it. And so the image on the left is from State Road 91 widening from Golden Glades to Broward County. So on this specific project, the client asked us to depict the overhead power lines, which you can see in the top left, the subsurface utilities, which we color-coded to match what type of utility was, whether it was gas, buried electric, sewer, all sorts of those. We tried to match the utilities with what they were. And we also provided the proposed aesthetics on the MSC walls and the bridge. For this client, the aesthetics were a really important public factor on this project, which makes sense why the client would ask us for a depiction of the bridge and wall aesthetics. The freehand 3D tool, modeling tool that Callie had used previously, was used to depict the bridge and wall aesthetics. As discussed on the previous slide, after modeling the proposed and existing utilities, you can then use the clash detection tool to check for horizontal and vertical clearances between the bridge foundations and your proposed utilities or drainage structures, or even roadways. The image on the right is from our FDOT pilot project. This graphic demonstrates sign structure erection in proximity to existing overhead power lines. The overhead power lines were modeled using the existing digital terrain model, or DTM, as well as LiDAR technology. We referenced that information into our OpenRoads file. Then within OpenRoads, we were able to create a transparent halo using the extruding tool around the existing lines, and we used those to compare against using the clash detection tool. The green halo represents compliance with the clearance requirements, and naturally the red halo represents non-compliance with the governing criteria.
One of the add-on programs that Bentley offers is called Prostructures. Basic Prostructures tools are now included in OpenBridge Modeler. The Prostructures add-on creates accurate 3D models for structural steel, metalwork, and reinforced concrete structures. It allows you to create design drawings, fabrication details, and schedules that automatically update whenever you change the 3D model. This program can develop plans, details, sections, and quantities and cost estimates. Concrete objects such as footings, columns, beams, and slabs are automatically recognized for the appropriate tool in Prostructures. We utilize this software on a turnpike project on the Heft from State Road 836 to Northwest 106th Street. We use the program to model and detail a concrete inverted T, which lends itself to complex rebar layouts where detailing and verifying clearance requirements is very complex. It should be noted that in order to utilize the clash detection tool in this situation, the applicable design criteria like AASHTO or the IBC you're trying to check the rebar clearance against must be manually defined in the program. The program does not currently have design criteria loaded into it. We ran the clash detection tool with Prostructures, and as you can see, the tool identified a clash in manually described clearance requirements, as shown by the red highlighted reinforcement. In the next slide, you'll be able to see where the red highlighted reinforcement was manually modified to a 180-degree hook. The clash detection tool was rerun, and the user input clearance requirements were met and no longer detected a clash. This program allows you to analyze in profiles, elevation, and cross-section views with solid and transparent options to help explore areas with complex geometry. You're on mute again.
Sorry about that, apologize. So that wraps up our example projects that we're going to get into in this presentation. And now we're going to transition more into a lessons learned, some tips and tricks, some challenges and stuff that we still see that we need to overcome before we fully transition to a full 3D model project as our only deliverable. And so with that, we're going to talk about bridge widenings first. So the first design challenge that we're going to discuss, like I said, is how OBD handles existing bridge information, DTM models, and bridge widening. So currently, designing a bridge widening in OBD is not as straightforward as you would want it to be, and can become quite cumbersome. So first, we'll discuss how traditionally a widening would happen and how OBD improves on this process, and then also the limitations that the software has. So previously, structural engineers relied on as-built and 2D survey to help determine existing bridge geometry. So for bridge widenings, the traditional process started with recreating the existing bridge in 2D CAD using the as-built plans, and if we were lucky, topographic information. We would verify cross slopes, super elevation transitions, beam elevation, bridge skews, substructures, and just really look at the whole bridge. We would then move forward in a traditional manner of bridge design, where we would design and define the proposed bridge widening that we had on that project. So with OBD, the early steps of design are relatively the same. You still have to define your existing bridge. You still have to go through some of those hoops that you have to jump through, and then you still have to design your bridge. However, we can now compare the existing bridge against 3D DTM models and LiDAR point clouds along with the as-built plan. So you get more information, you get more accurate information, so you can really lock in your existing bridge. And then you can compare, once that's confirmed, you can compare it against what you see in Google Earth and images and site reviews. So when confirmed, the existing model is complete, you can then use it for final design of your proposed widening. For the existing bridge model, the DTM of the bridge deck surface will be utilized to establish the existing top of deck elevation, the bridge crossslope, the coping limits, and the begin-end bridge limits. This refinement in a 3D environment improves the accuracy of the existing beam locations, top of deck elevations, substructure geometry, orientation of exposed pile foundations, as well as proposed drainage, existing drainage, and proposed existing utilities. These are all very important key elements in a typical bridge widening project. You have to know where all that stuff is. Knowing and seeing the locations of all aspects of a project allow the design team to better identify constructability issues like crane placement or other geometric conflicts like your foundation with a proposed utility or an existing utility, which is even worse. So knowing where that stuff is very, very important. OpenBridge is best when modeling and designing a new bridge, but bridge widenings pose more challenges like I had alluded to. The existing bridge typically has different properties or dimensions than the proposed bridge widening. For example, the material properties, deck thicknesses, beam types, they can all differ within an existing bridge, and almost always they're going to differ from your proposed bridge widening. This is where we see the biggest limitation in OBD. For design purposes, the program has limitations on the different material properties within the design software. So in order to work around this, you must model multiple bridges in units. As I show in this slide, we modeled the existing bridge in one model, and then we modeled the proposed bridge widening, and we split those in 3 models, as you can see on the bottom image. And then we're able to reference all of those things into one. So after we model the existing bridge with its unique properties and your proposed bridge, you can then, like I said, model everything into one master file so that you can view your complete model. From this model, plan sheets can be developed as well as getting an overall view of your bridge widening. In this case, we're widening both inside and outside of the existing bridge. You can also export your model as a KML to get a good look at what your bridge will look like in context of the true world and how your bridge compares to the existing bridge. So if you want to compare existing bridges, exporting to Google Earth and seeing, just making sure everything kind of lines up is always a good idea. Keep in mind, one benefit to having the files separated when progressing from modeling to design is that the existing conditions are typically unnecessary to design the proposed or new bridge. And like I said, you then progress into final design. But like we said, the biggest issue with this approach is the file can become very big, and sometimes it'll lead to corruption of the file or a lot of crashes. And so if you have a lot of bridge widenings or a lot of different models that you're referencing in the one master file, it's going to get quite large, and it becomes very difficult to manipulate and use. So as Callie described earlier, OpenBridge Designer combines OpenBridge Modeler with their design software like Leap Steel or Leap Concrete. The program also combines several supplemental programs that Callie got into one product, which reduces repetitive data entry and repurposes data for plans production and analysis purposes. One important item we wanted to highlight was when you're using the software and you go to exporting from your bridge model to your analysis software like Leap Concrete or Leap Steel, you will receive the model transfer report. The model transfer report is a report summarizing all the assumptions and translations between the different programs. So we really wanted to highlight this because it's very important for all parties to review and be comfortable with how the programs are communicating and translating. So our suggestion is when you first start using the program is to perform additional checks and reviews to verify geometry and translations between the various programs. Another lesson learned that we were able to identify on one of our projects with Central Florida Expressway Authority, or CFX, we were designing and modeling a 3,200-foot long bridge. It was supported by Florida I-beams, and we had intermediate pile vents as our substructure. So after modeling the bridge in OBD, as you can see in the picture on the bottom, we exported the model to the design software, Leap Concrete, and specifically we're going to highlight the ConSpan program, which we used to design the superstructure. However, once we exported to the design software in ConSpan, we noted that the bridge barrier wouldn't come in at the right location, as you can see in the picture on the top. So with that being said, we're unable to get the truck and lane live load generation, so we were unable to utilize the software for superstructure or even substructure design. We notified Bentley and we did a lot of coordination, sharing files, and they agreed with our result here, and they acknowledged the defect, and they expect to release a new update to Bentley here in the next couple of days, and they will be addressing this issue. So one other issue on the same project, same CFX project, same bridge, 3,200-foot long fib bridge, is when I went to report the input and output superstructure data. I would go to run the input report for the bridge on all 32 spans, and would only document spans 1 and 2 as having the full number of beams, which was 6. And then the remaining 30 spans would only show 2 beams. So but then when I would run an output results report, all 6 beams were accounted for. So it was only kind of localized to the input report. So we coordinated with Bentley, they acknowledged the issue, and like I said, in their next update, which is expected in the next couple of days, they will be addressing this issue. So in the meantime, there is a known workaround. As shown in the image on the right, you can select a different default span, then reselect the first support line to validate. Then save your file and generate the reports again. All 32 spans and all beams were accounted for within the input and output reports.
One of the important topics that we wanted to cover was planned production capabilities of OpenBridge Designer. However, it's still in early steps of development. FDOT has released their CAD and design manuals for the FDOT workspace, which is currently available in its beta version. However, like David mentioned earlier in the presentation, the plans production process has not yet been finalized nor perfected. The image found at the top of the page was created through OpenBridge Designer. We use the tool called Create Superstructure Cross-Section Drawing under the Analysis and Reporting ribbon. As you can see, it does a pretty good job at creating a section through the bridge deck and exporting the bridge geometry. The beta FDOT OBD workspace release is not intended for production, so in the meantime, this baseline work can then be copied into an FDOT CAD workspace, manipulated and modified to meet the FDOT CAD manual standards. Similarly, substructure and foundation baseline work and base files can be developed using the Create Substructure Drawings tool found under the same Analysis and Reporting ribbon. Again, like the superstructure, additional manipulation will need to be performed. OpenBridge Modeler and OpenBridge Designer allow you to generate detailed reports as well as create 3D models and 2D drawings for plan views, section views, and elevations. The image on the left is from the same CFX 3,200-foot long bridge supported by intermediate pile vents that David has previously mentioned. We then selected the view, section, and details we wanted in the plan sheet using the FDOT workspace. The image on the right was produced from the OBD model using the FDOT workspace, and depicts the concrete intermediate bent plan view, elevation view, section view, dimensions, and view details. Like I previously described, you would then need to manipulate the resultant CAD to conform with your applicable client requirements.
So now we're going to talk about some of the miscellaneous challenges that don't have to do specifically with the program or are as detailed as some of the design stuff going on. They're more of the big picture stuff. So anytime an industry shifts towards something new, there's always challenges and obstacles to overcome. One of our biggest obstacles is the learning curve associated with any new software, new design, and analysis process. We've encountered a little bit of a hesitancy in fully adopting a 3D model as the main source of design and plans production, as this is very different than the traditional method. Although we found, as with any new design process, that once you're able to compare the model with your existing processes or analysis, like you're able to compare the results from the 3D model with the results of a traditional method, the hesitancy in adopting this begins to dissipate. There's also the obstacle of staying up to date with the most recent developments in this new and developing advancing technology. We've also found issues with using newer and older versions of the same software. So obviously, like we had kind of talked about previously, Bentley's releasing new updates. And so we've experienced when coordinating files with other consultants or even within our own company that if everyone's not on the same version, that you do have some issues and files can become corrupt. Something to note as well is that OBD files are not currently compatible with MicroStation, so you can't reference OBD or ORD files into MicroStation. It should also be noted that the currently available OBD design criteria is using the 8th edition of AASHTO. The next Bentley update will allow for bridge design in accordance with the 9th edition of AASHTO. But then you have the issue that the FDOT workspace that's available to everyone now does not work with the soon-to-be future OBD release. But FDOT is working with a beta version of OBD's soon-to-be released version, and they want to make sure that they have a compatible workspace shortly after the Bentley update. Another challenge is developing an accepted form of QA/QC. Most government agencies, as well as the Florida Board, are investing resources to develop an accepted and uniform QA/QC process that demonstrates supervision, checks, and quality assurance. We must make sure these processes ensure the highest quality and safety expected from the traditional non-3D design and plans production. The Florida Board of Professional Engineers has recently developed a task force dedicated to 3D and ensuring supervision, liability, and ownership for engineers of record. The Florida Board completely understands the FDOT's desire to ultimately make 3D models the contract document, so the board is currently advancing discussions on proposed rulemaking.
To summarize the highlights of our presentation, there are a number of great benefits to utilizing OpenBridge Modeler and OpenBridge Designer, including converting roadway and bridge information into graphics, videos, and 3D PDFs. The program helps you visualize in 3D, 2D issues or conflicts commonly missed. There's automatic data transfer between the disciplines. You get to see your bridge in context of the real world. You're reusing and repurposing data, which results in time and cost savings. And lastly, you get to leverage existing MicroStation capabilities like GeoPack and coordinate geometry to create accurate bridge models that update and change as the roadway information changes. Some of the challenges we've experienced are the FDOT CAD manual criteria being integrated into OpenBridge Modeler and Designer. There are learning curves that need to be overcome in order to continue designing in 3D. The Florida Board of Professional Engineers, as David had mentioned, still need to sort out how to delegate and document EOR responsibilities, as well as figuring out how to perform peer review, checks, quality control, and assurance. As we noted, there are also some design limitations that we discussed, including bridge widenings, utilizing existing topographic information and LiDAR, and cross-software program communication.
So with that, unfortunately, we are pre-recording this, so there's no live Q&A session. So we wanted to at least bring up 2 questions that we typically get from when we do this presentation in front of a live crowd. And one of those is, how long is the learning curve for the software? It's a typical question we get from a lot of people. And so we've seen in our experience somewhere between 3 to 6 months, depending on the willingness of the person learning. Some of our chief engineers who have been doing this for 30 or 40 years are very committed to the traditional process of roadway and bridge design. And so, but like we mentioned previously, we've seen that hesitancy begin to dissipate once they're able to perform their own independent checks on geometry and the results. And, so that's something very important to note. One other thing is that when you are beginning to use the software and learning is that you can continue to use MicroStation in the 2D sense. So for a bridge layout or roadway layout, you can go do your typical section in the 2D top-down view, and then you can reference that MicroStation file into ORD or OBD, and then go to the top view of your 3D model and make sure that line work is just laying right on top of each other. And that's one way to make sure that you're getting what you're expecting. And one of the other things that we get a lot is what kind of training do we do at WGI, and how long does it take? How much should we invest? And so, we do have, FDOT has a manual on OBD and ORD training. And so that's very, very helpful when first using this software. It goes into ORD, OBD. We did a lot of hands-on training here at WGI. We do monthly lunch and learns, whether it's, an hour month or an hour lunch where we go through some of these lessons learned. There's also a lot of Bentley videos. And so, there's a lot of resources out there to train your staff and get up to speed with this software. So with that, Callie and I just want to thank everyone so much for attending WGI's presentation on OpenBridge and OpenRoads, a 3D design and real-world FDOT application. Thanks, everybody.